And then there's the abiotic. So your temperature, all right, that's going to control the rate at which different biological processes can happen. The salinity and water availability, how much osmosis can happen between cells, your sunlight. All right, we'll talk in a moment about how that sunlight really dictates a lot of our climate, and then as a result dictates a lot of particularly the plant life that can be there, because your sunlight's necessary for photosynthesis. And so if you're not getting as much sunlight or as much direct sunlight, that's going to affect how much photosynthesis can happen, which then in turn determines the amount of plant life that can live there. And of course, us as organisms, as animals, are going to be affected as well. There's also the idea of behavior. All right, a lot of organisms are very sensitive to photoperiods, how much light is around. Do they hibernate? Do they not hibernate? When do they sleep? So a lot of behaviors are very dictated, very affected by the amount of light in the environment. Wind's going to be another one. All right, and that wind can really amplify the effects of temperature. All right, either increasing the heat if there's not a lot, losing a lot of evaporation and condensation, convection, when there is a lot, changing the morphology of the plants like you see with the picture there. Okay, and so all of that's going to have an effect as well. Your rocks and soil, all right, particularly their structure, their pH, composition, all that kind of stuff, really plays a huge role in the plants. A lot of these abiotic factors really start with the effects on the plants, and then those effects kind of trickle into the animals that feed on them. And then just climate in general. What's the prevailing kind of weather conditions in that particular area? And that's kind of where we're going next. So when we talk about climate patterns, we're talking about your temperature, your water, your sunlight, and your wind. All right, and remember when we talk about climate, we're talking about major overarching patterns. We're not talking about your day to day weather. All right, so it's sunny today and rainy tomorrow. Those are your weather patterns. But overall, what's the average rainfall for the year? What's the average temperature for certain seasons, or do they not have seasons? That's the kind of stuff we're talking about when we talk about climate. And we can talk about it in a macro level. So, what are these patterns globally, regionally, locally? Or we can go all the way down to those microclimates where we're really looking at very fine patterns within an ecosystem, say under a fallen log or in certain levels within a stream or a small pond or something like that. That determines very small scale differences in those abiotic factors. One of the classic examples is the kangaroo rat crawling into its hole during the day. All right, and it's much cooler, much damper within its little tunnels and within its little habitat underground versus what's going on macroscopically at the surface. All right, so try to keep those two in mind when we talk about these patterns. So, where do all these patterns come from? Well, it really gets determined largely by the amount of solar energy that's coming in. So, the light, the heat that we get from the sun. And overall, that heat, that infrared radiation, if you will, gives us a warming effect on. And the amount of direct sunlight that we get determines the kind of variation in temperatures we see. And those variations then drive evaporation and circulation of air and water currents. And that's why we start talking about the distribution of different organisms and different biomes, because it all comes down to the amount of sunlight we get. So if we take a look at the picture, your most direct sunlight's coming directly at the equator. All right. Whereas we get to higher angles, both in the North and South Pole, All right, it's much more diffuse. It's much more of a low angle rather than being direct head on. All right, and so those variations in intensity are due to the curvature of the Earth and all of that. And so your intensity is strongest here and weakest as you get towards the poles. And so all of that drives then these currents in our air, which then we'll see drives the currents in the water. And those play a major role in why we see different climates, different biomes within our globe. So if we take a look, right, we said 0 degrees is where we get the most direct sunlight. And that sunlight's going to help to heat up the atmosphere. The warmer the air, the more moisture it can hold. So if you think about it, the biomes, the climates you're used to seeing down here around the equator are very warm, very wet, and they're like that all year long. Well, they're picking up moisture off the oceans and throwing it up into the atmosphere. All right, and so we get this very warm, moist air, all right, and the warmer the air, the more it's going to rise up into our atmosphere. But as it does that, it's going to start cooling off. While the cooler you get, the less moisture that air can hold. And so you get a lot of rain and a lot of precipitation there at the equator because it's picking up all that moisture, pulling it up into the atmosphere, cooling down, and dropping all the rain back. So, all right, air's cooled off, it's dropped all of its moisture, and now it's going to end up creating these convection cells, all right, which is what you see here. And so now I've got this very cool, dry air. Cooler air is going to start to descend, and now here you get these arid regions, aka your major deserts are right around 30 degrees north or 30 degrees south because of these air currents. All right, so wet, moist air here at the equator, as it warms, it's going to drop that moisture because it can't hold on to it. And that dry air then flows. It's cooler, so it's going to start to sink, warm back up. All right, and this whole cycle starts all over again. Okay. You also have sort of these trade winds, if you will. All right, so we've got these convection currents going up into our atmosphere, but then we also have wind currents within that. And those are really driven by the rate at which the Earth is spinning. All right, so our land near the equator actually moves slightly faster than the land at the poles. Okay, and so we sort of have this spinning kind of top idea almost. And you get these deflecting patterns in what we call our easterlies, westerlies. Your major wind currents. And so you get these cooling trade winds that blow from east to west in the tropics. All right. And you get those prevailing westerlies that kind of blow from west to east. So if you look at our zone, which is a temperate zone, and you ever watch the weather guys on TV, and they're talking about your jet stream, and all of our weather patterns always end up from the west coast and blow across the country and onto the east coast. And all of that's coming from these wind patterns that we're seeing because of the way the Earth is rotating underneath. Okay, so that's kind of where that comes from. We also have seasonal changes here. And those seasonal changes come from the fact that the Earth isn't straight up and down. We're on a tilt. All right, 23.5 degrees to be precise. And so what ends up happening as our Earth is revolving around the sun, we get variations in the intensity of the sunlight and that solar radiation that we see throughout the year. So your equator is pretty much getting intense sunlight all year, but as you get further up, you get that less intense, less direct sunlight, but that's going to shift just ever so slightly as the sun goes around, or excuse me, as we go around the sun. And so you get these belts of sort of that wet and dry air, all right, these belts that we see here. And as we revolve around the sun, you see those belts kind of shift either a little further north or a little farther south as we revolve around the sun, and those angles change slightly due to our seasons. All right. So I'm going to encourage you to take a look at the seasons video that I'm going to post for you. And it's going to go into a little bit more detail to kind of give you an idea of how all of this works. They do a really great job at explaining that. So take a look at that video. All right, I suggest maybe you pause here and go ahead and take a look at that and come back. So in addition to getting those wind patterns, we also then get a similar effect within our oceans and getting ocean currents. And those ocean currents are really kind of fascinating when you start taking a look at the effects that they have on the land nearby. So if we take a look at something like the Gulf Stream, which is coming up from the Gulf of Mexico, all right, up our coast and over into Europe, all right, we're about here. So take a look at where that falls in terms of latitude on Earth. And take a look here where England is. And for any of you who've maybe ever gotten the chance to be there or just kind of have an idea, their climate is relatively similar, particularly temperature-wise, to us. And yet we're down here, and they're all the way up here. They're much higher up on Earth than we are. But because they're getting all of this warm air from the Gulf Stream, it's helping to moderate their temperature and keep them a little bit closer to us rather than being what you would assume to be much colder, because here's your Arctic Circle. All right, that's pretty cold. Then you've got the California current, which is kind of doing the opposite. So any of you who have had any experience with Southern California, they've got a much more moderate climate, even though here's your equator. They're much closer to the equator than we are, but they don't experience nearly the amount of temperature shift. They're talking mid-80s pretty much all year long because they're getting cooler air, or excuse me, cooler water coming down the coast, all right, and that helps to moderate them. So you see a lot of that in different areas throughout the globe in terms of keeping them warmer or cooler based on where the water near the land is coming from. And so here's kind of what we're talking about on a smaller scale. Those large bodies of water really have a major effect on the local climate. Remember that water has a very high specific heat, so it can kind of be your heat sink during the day when you need to kind of absorb lots of heat to keep your land from overheating, all right, but then it kind of gives it back in the evenings when you don't have the sun to keep it as warm, all right, and so you get that warm air that kind of rises up over the land, all right, and as it cools at the higher elevation, it's going to sink again, it's going to pull off heat from the water and help to cool off the land again. So what you're getting here is a much more moderated temperature than you would if this was land here rather than water. All right. Your mountains also have a major effect on climate. All right, so here is Southern California. All right, we've got the Pacific Ocean. We said we've got those cooling currents coming down the coast. So as that warm air kind of rises, it's going to pick up moisture off the oceans, dump a lot of moisture here, so you get a relatively moist environment. But as that wind picks up, all right, it's going to drop whatever moisture it still has on this side of the mountain. So you kind of get what they call these rain shields, where as that air rises, it can't hold on to any of that moisture anymore. It's cooled off, it's high enough, and so it drops all of its moisture on this side of the mountain, all right, these rain shadow sides, and as it picks up and cools back down again, now you've got these deserts. So what's on the other side of the Sierra Nevadas? Well, that's where you get things like Las Vegas. All right, and if you've ever seen Las Vegas, it's very dry. Okay, it is a desert. So that's sort of what we're seeing here, is that those mountains are causing more local distribution of different ecosystems because of weather patterns, the wind patterns, the local climate patterns that you're seeing. Okay. We also see it within the lakes themselves. Okay. So a lot of bodies of water have these boundaries called thermoclines, where they really separate out the warmer water up top. All right, here's your thermocline. Your warmer water up top, here's the thermocline in the middle, and the cooler water down bottom. Now, oceans aren't as susceptible to this, but your lakes, all right, often get what they call seasonal turnover because they're so sensitive to those changes in temperature that we experience as we go from winter to spring. So here's your turnover. Or from summer to autumn, and here's your turnover again. Okay, so you get a kind of warmer layer here in the middle, real cold water down here, and still cooler water up here because it's wintertime. We get that seasonal turnover, and now you get all the warmer water up here, sort of a middle layer here, and all the cold water at the bottom. We turn over again, and the process cycles over again. Okay. These are incredibly good for those lakes because as they turn over, not only are they changing sort of temperature gradients, but they're picking up and cycling through both oxygen and other nutrients that are stuck here at the bottom, flipping them so that you get this turnover and this sort of churning of all of those nutrients from the bottom every year. And that's really important for the organisms that live there to get that sort of cycling within their own little ecosystem of that oxygenated water, of that nutrient water, so that they're able to get what they need. So one of the things that we're studying more at a global region is climate change. All right. And what we're really concerned about at this point is sort of trying to predict what sort of warming or even cooling effects that we're going to see over time, and how is that going to end up affecting the distribution of organisms, particularly the ones like your plants that can't really pick up themselves and move. All right. And so if we take a look, one of the things they're looking at in terms of some of that overlap versus predicted range versus current range for organisms is, all right, if we warm 4.5 degrees over the next century, here's what we're predicting to see. If we do 6, now that distribution gets even bigger, right? And what's that going to have an effect on both the animals that can pick themselves up and move, so they're able to adapt a little bit more, versus organisms like our plants that can't, and also the interactions between organisms that currently live up here and now we're spreading out potential ranges, and what's that going to do to what already is there? All right, and is that going to push them further? Are you going to have some more competition in here? Are we potentially going to kill off organisms? Do we think they can adapt, so on and so forth? So that's something that they're looking at.